All right, welcome to this explainer. Today we are tackling one of the absolute most frustrating issues we run into when dealing with massive log volumes. If you've spent any time working with observability platforms, you already know log management is crucial. But waiting endlessly for those queries to load, it can feel like a massive bottleneck. Well, today we're going to fix that. We've all been there, right? You're staring at your Grafana dashboard during a critical 3 a.m. incident, only to be hit with this dreaded error message. Content deadline exceeded. Your system is down, you need answers right now, and your logging tool just timed out. It's incredibly stressful.
So, what's the deal? Why do some logQL queries come back in literally milliseconds, feeling practically instant, while others just hang there and completely crash? To really answer this, we need to take a step back and look at what's actually happening under the hood the second you hit Run Query.
First up, let's peek inside Loki's architecture and see how indexing metadata builds the foundation of its entire design philosophy. See, unlike traditional log management systems that build massive, super computationally expensive full-text indexes for every single word in your logs, Loki flips the script. Its core philosophy is actually index little, grep a lot. It deliberately trades query time compute for storage time simplicity. This means it only indexes the metadata, the labels attached to a log line, and stores the actual log content as highly compressed chunks in object storage. This approach will save you an absolute fortune in storage costs.
Think of a query in two distinct phases. First, you've got the discovery phase. This uses label filters for a blazing fast, inverted index lookup to find the exact right chunk of data. Then comes the execution phase. This uses line filters, which is where Loki literally decompresses those chunks and does a brute force grep, scanning line by line for your specific text. The secret to speed? Making sure that first discovery phase does most of the heavy lifting.
But here is the catch. High cardinality is literally the silent killer of Loki performance. Cardinality is basically the number of unique combinations of your label names and values. If you use dynamic labels, like attaching a unique user ID, an IP address, or an exact timestamp as a label, you completely blow up the index. This forces Loki to create millions of tiny, uncompressible chunks. When you run a query, Loki has to open every single one of those tiny chunks, and boom, content deadline exceeded.
Moving on to the logQL evaluation order, let's lay out the golden rules for writing queries that actually finish on time.
Loki is strict. It evaluates your query exactly from left to right. No exceptions. This means you absolutely must narrow down your data in a very specific sequence. First, use your stream selectors. Those are your index labels. Second, drop in a line filter for a simple text search. Third, use a parser to structure whatever data is left. And finally, apply a label filter on that parsed data. If you mix this exact order up, you're basically forcing Loki to do a ton of unnecessary work.
The biggest takeaway here: always filter before you parse. Parsing things like JSON is really computationally heavy. If your query pulls all the logs for an app, parses every single one of them as JSON, and then looks for a 500 status, it's going to be incredibly slow. Instead, pull the app logs, do a lightning-fast substring search for the text 500, and only parse the tiny fraction of logs that are left over. That second method is exponentially faster.
Let's actually see this in action. We're going to do a live query speed comparison using real log data right inside Grafana Play. That's play.grafana.org.
When you compare an unoptimized query to an optimized one side by side, the difference is wild. An unoptimized query often relies on a CPU-heavy regular expression across a massive, broad environment label. CPUs absolutely hate regular expressions. An optimized query, however, isolates the specific service to narrow the index lookup and then chains together simple, fast substring matches. A simple substring search will beat a regular expression every single time.
Just by rewriting the query to leverage the index and use simple line filters first, we're talking about a massive 99.7% reduction in the amount of data scanned. According to some recent needle-in-the-haystack benchmarks shared at GrafanaCon, optimizations like this can take a query that previously had to scan 3.5 terabytes of data and shrink it down to a measly 8 gigabytes.
And what's the real-world impact of that reduction? Well, a query that originally churned for over 4 minutes and ineditably timed out now executes perfectly in under 3 seconds. Literally the difference between a total panic attack and a calm, controlled debugging session.
Let's put this into practice with a real-world support scenario. How do we find one specific needle in an absolute haystack of data?
Picture this. You're a site reliability engineer trying to trace a specific failed transaction UUID in a payments microservice. The catch? This single service is generating over 1 million long lines every single hour. You have to find one exact string of text in all of that noise.
Now, your very first instinct is probably thinking, hey, I'll just make the transaction ID a label so I can query it instantly. Stop. Do not do that. As we just talked about, unbounded data like a UUID will completely wreck your cluster with high cardinality. Every unique transaction ID would create a new log stream, leaving you with a bloated index and terrible performance.
Instead, leave that UUID right there in the unstructured log text and follow a systematic approach. First, shrink your time window in the UI. Don't search a whole day if the error happened 10 minutes ago. Next, use static labels to isolate the streams. Toss in a fast substring filter to brute force search for that exact UUID. And lastly, only parse the JSON at the very end if you genuinely need to extract more fields. When you put it all together, it's actually incredibly elegant. You use your static labels for a lightning-fast index lookup to grab just a handful of chunks. Then, your rapid text scan rips through only those specific compressed chunks. It safely finds that highly unique identifier in milliseconds, and your storage costs stay completely safe.
So, I've got a challenge for you. Open up your Grafana dashboards right now. What is your absolute slowest, most expensive logQL query, and how can you reorder it today? Apply this strict left-to-right evaluation logic. Use specific labels, ditch the regex for simple text filters, and always filter before you parse. Watch your query performance absolutely skyrocket. Thanks for hanging out for this explainer. Now go optimize those logs.